Welcome to this video. We're going to be talking about proof by mathematical induction. And this is aligned with mathematics and analysis and approaches, higher level standard 1.15. So what is proof by mathematical induction? Well, proof by mathematical induction works kind of like the domino effect. If you can prove something's true for the first case, n equals 1, like the first domino, and then show that assuming it's true for some domino out in the middle of nowhere, implies that it's true for the next one, then you can actually show it's true for all positive integers. So it works like a domino, showing for the first one, implies the next one, knocks over the next one, next one, all the way to all positive integers. Here are the steps we need to prove using mathematical induction any statement. So we say in general P of n is a statement. Step one is we need to show that P of 1, or the very basic step, is true. Step two is we need to assume that P of k is true. In other words, some random case, k is true. By assuming that's true, through some algebraic manipulation, we need to show that that also implies P of k plus 1 is true. If we can do that, then we can claim that it's actually true for all integers, positive integers, by the principle of mathematical induction. All right, let's try an example. Use mathematical induction to show that 11 to the n minus 6 is a multiple of 5 for all positive integers n. So our statement, P of n, is that 11 to the n minus 6 is a multiple of 5. And we're going to prove that that's true for all n. So we need to first prove it for P of 1. So for P of 1, we have 11 to the 1 minus 6. Well, 11 minus 6 is 5, so that is true. It is a multiple of 5, because obviously 5 times 1 is 5. Now let's assume it's true. Assume P of k. We have that 11 to the k minus 6 is a multiple of 5. In other words, equals 5 times some integer m. And I'm going to write where m is an integer. Okay, so we're going to say consider when 11k plus 1 is minus 6. Now we can't say equals 5m because we need to show that. So here's how we're going to do it. So 11 to the k plus 1 is the same thing as 11 times 11k and then minus 6. So remember that we said in our assumption that 11k minus 6 equals 5m, where m is some integer. Well, that also implies that 11k equals 5m plus 6. Now I'm going to use this fact, and you always have to use your P of k step. And I'm going to plug it in for 11k. So right here I'm going to get 11 times 5m plus 6, and then minus 6. Simplifying a bit, this is 55m plus 66 minus 6, which equals 55m plus 60. Well, 60 is divisible by 5, and 55 is divisible by 5. So therefore, this whole thing is divisible by 5. So we just showed that P of k plus 1 is also true. Therefore, we can say, therefore, by PMI, true for all integers. All right, let's try one more example. We're going to use mathematical induction to show that the sum of the first n terms of an arithmetic sequence with first term u1 and common difference d is given by this formula. So in other words, we're trying to prove, so our P of k, we're trying to prove that u1 plus u2 plus u3 plus all the way up to un is going to be equal to n divided by 2 times 2u1 plus n minus 1 times d, or that formula right there. Okay, so we're going to first prove the first step, the basic step, P of 1. So with P of 1, we have u of 1 on the left-hand side, and I want to show that that has to equal the right-hand side. Well, 1 divided by 2 times 2u1 plus 1 minus 1 times d, plugging in 1 for n, equals 1/2, and then my term here is going to cancel because 1 minus 1 is 0, times 2u1, which equals u1. So that's the right hand side, and clearly the left hand side, which is also u1, equals right hand side, so the first step is proven. Alright, the next part is to assume it's true for p of k. So we're assuming that u1 plus u2 plus u3 plus all the way up to some uk is equal to k divided by 2 times u1 plus k minus 1 times d. So notice I just substituted k into the formula. Okay, so now we're going to say consider p of k plus 1. And we're going to try some algebraic manipulation to get it to equal my right hand side. So first let me write this out. u1 plus u2 plus u3 plus dot 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 uk plus uk plus 1. Now I'm not going to say it equals k plus 1 over 2. I'm going to try and show that. So let me write that over here. My goal here is to get it to look like k plus 1 over 2 times 2u1 plus k plus 1 minus 1 would just be kd. So this is my goal here. I want to get to this in the end. And I want to also remember something. Remember that any term is given by u1 plus n minus 1 times d by the explicit formula. So I'm going to need both of those facts here. Okay, going back to here, we notice that actually this first part here, all the way up to uk, we already know what that equals. We're using our induction step. And keep in mind, you always have to do that. So I know that equals k over 2 times 2u1 plus k minus 1 times d. And then I got to tag on my u of k plus 1. So I want to make that look like my goal. So let's remember that by the formula, uk plus 1 has to equal u1 plus k plus 1 minus 1. But let me just write it. K plus 1 minus 1 times d. In other words, u1 plus kd. So I can substitute that in. So this is really equal to k over 2 times 2u1 plus k minus 1d plus u1 plus kd by the substitution that I just made. Okay, so there's no perfect way of approaching it from here on out, but keep in mind I want to try and make this look like my goal, and if I can do that, then I show by the PMI that this is true. So you can approach this different ways, but I'm just going to FOIL everything out and then re-simplify. So starting with k divided by 2 times this term and then times this term, you get u1 times k plus k times k minus 1 times d over 2, and then that's plus u1 plus kd. Okay, simplifying further, notice that this term and this term are like terms. This one has a coefficient of 1 and this has a coefficient of k. So when we combine those two, it actually becomes k plus 1 times u1. Alright, so I'm off to a good start. Now let's deal with this part. Foiling that out, it actually equals k squared d minus kd. And also this right here, kd, is actually the same as 2kd over 2. And the reason I did that is because I want the denominator here to match the denominator there. So we get k plus 1 times u1 plus k squared d minus kd divided by 2 plus 2kd over 2. So you can see things are starting to form together here. So I'm going to jump over here to the bottom left. I've got k plus 1 times u1 plus k squared d plus 2kd. kd and 2kd will cancel and give me just positive kd. So this equals k squared d plus kd over 2. Okay, so that's going to equal k plus 1 times u1 plus, I can unfoil here, and this is actually equal to k times k plus 1 times d all over 2. Okay, notice that there's a k plus 1 term here and a k plus 1 term here, and I'm also going to pull out the 2 because remember I'm trying to make it look like my goal. Okay, so this is going to give me k plus 1 divided by 2 times 2u1, because the 2 here and the 2 in the denominator have to cancel to give me just u1, plus kd. In other words, I've done it. I've made it to the goal. Now, that was a lot of algebraic steps, and it's often going to take a lot of algebraic steps to prove by mathematical induction, but there's no perfect route. As long as you can get it to the end and you've done it without doing any illegal moves, then you've done it. So I can now finish off by saying, therefore, by PMI, Pn is true for all integers. All right, and that's it. So go ahead now and try some practice on your own.